Uh, this will be on the quantum measurement problem. And I request Professor Dipankar to chair the session, yes.
Can you hear me? Okay, okay. So good afternoon, everybody, and good morning, Adrian. He's joining us from UK. So this is a special session on a very special topic which occupies a center stage in the whole discussions, in the entire discussions on foundations of quantum mechanics. And I shall just spend a couple of minutes giving some historical remarks to set the stage. To set the stage for these discussions with a bit of historical remarks. Okay. So it was in 1925, on 11th July, that Heisenberg gave Max Born, after he has spent a summer vacation in Heligoland, the draft of his original paper on quantum mechanics, which was titled The Quantum Theoretic Interpretation of Kinematic and Mechanical Relations. And after he was then working with Max quantum mechanics, Heisenberg's original paper by none other than Einstein. This is not much known here. So July, as I mentioned, July, Heisenberg gave Max Born the manuscript, and then he went to Berlin to give a talk on his new work, and Einstein was there. And after the talk, he took a long walk with Einstein, and that discussions during that talk left a deep impression on Heisenberg, and he spends an entire chapter of his wonderful autobiographical book called Physics and Beyond on this particular discussion with Einstein and the various points Einstein raised. So I would strongly recommend everyone to read it. Now, there Einstein's central objection was concerning how do you describe the process of observation? How do you explain the occurrence of particle tracks in a cloud chamber? And so that is really the quantum measurement problem, how quantum physics can account for the occurrence of a definite result whenever we perform a particular measurement. So on this central riddle, after 100 years of that fateful discussion between Einstein and Heisenberg about the problem, we'll be hearing from two of the leading experts of our times who have spent many years thinking about this issue, writing on this issue. One, Adrian from the University of Cambridge, and the other one, Professor Nicolas, whom the audience have already heard him, and he has been introduced there. So I shall not introduce Professor Gisin anymore, take your time. Adrian Kent is in University of Cambridge, and he holds a distinguished visiting chair at the Perimeter Institute for Theoretical Physics, and his range of contributions from quantum information theoretic applications to foundations of quantum mechanics, and is very well known in his field, and I do not want to spend time talking about his contributions. So both of them are very well known. So let us straight away begin with Adrian's talk. It will be 45 minutes, followed by Nicolas' talk, and then we'll have a coffee break as usual, and then the discussions. And since this is a very contentious topic, which each from very strong views, many physicists, working physicists dismiss it as a philosophical curiosity. On the other end, on the other extreme, there are physicists who are working on experimentally testing aspects of this problem. So we have a strong divergence of view, and so we are looking forward to an exciting discussion, stimulating discussion after these two talks. So Adrian, please go ahead.
Thank you very much, Dipankar. I just need to... Now, can you see my slides? The slides visible? Yes, good. Okay. So many thanks for including me in this meeting. It's a great privilege to be part of this, and I'm really looking forward to the discussions. I'm particularly happy to be co-presenting with my old friend and colleague, Nicolas Gisin, and I hope between us we can give you a variety of perspectives on the measurement problem, or as I prefer to call it, the quantum reality problem. So let me start with that point. Why do I speak about the quantum reality problem rather than the measurement problem, which was the traditional terminology? Because potentially, at least, the focus on measurement, which is we normally think of as something that humans do to quantum systems, is overly narrow and misleading. There's a problem in trying to make sense of quantum theory in context, regardless of whether humans are present, regardless of whether apparatuses are present. What we really want, at least to my mind, is an account, a version of quantum theory that allows us to understand and describe how the quasi-classical, the approximately classical world around us arose from a cosmology that initially didn't have classical structure. And to describe that without talking directly about observers or artificial measurement devices, which surely, almost surely at least, didn't play a central role in the fundamental way of understanding that emergence. So, as Dipankar's already mentioned, the whole topic is controversial. There are many physicists who are not concerned about the quantum measurement problem, and they will give you reasons why people like me and many of us here are misguided. One of them, one straw man motivation is that we really are so in love with classical physics that we somehow want to restore a classical way of thinking. I think that's not true of any colleague that I know of who works on quantum foundations these days, but it's still out there as a straw man accusation. Spending too much time talking with philosophers, that's another big concern of some of our colleagues, that we've somehow lost sight of what it means to be a physicist and become hung up in metaphysics. Or, yeah, it's sharpest, just an inability to understand quantum theory. Somehow we're not getting the point of quantum theory. If we did, then we wouldn't be worrying about measurement or reality. And there's a sort of sharpened version of that last one, which is, I guess, the closest to the mainstream way of dismissing the measurement problem, which is that we, the people who are not Everettians, don't understand the elegant simplicity of many worlds quantum mechanics. Although it's been explained by successive authors since Everett, and I've listed just a few of them here. And maybe they're being charitable, they think we're a little bit confused because we worry that multiplying universes is an extravagant thing. And we should focus instead of postulates. Everettian quantum mechanics has fewer postulates, and that, to their minds, makes it more elegant. I don't want to spend very long on Everett because any discussion of Everett can fill an entire meeting on its own. I just want to say there are many thoughtful people from Einstein onwards on the other side of the argument who don't think that any collection of Everettian ideas works, would argue that we need a one-world ontology for quantum theory rather than a many-world ontology. And my view is aligned with theirs. In particular, I think there's no combined solution of the problem of probability. How do we actually make sense of the role of probability in what is a deterministic version of quantum theory, many worlds quantum theory, combined with the problem of structure? How do we talk about probabilities along with the emergence of quasi-classical branches? And actually also, many worlds theories are a very different type of beast from standard scientific theories, and they don't give any evident way of scientifically confirming them. There seems to be nothing you could do that would, in any standard way, give you more or less evidence about whether you lived in a many worlds universe. This is my view. I know many respected colleagues disagree for a variety of reasons, but I want to leave the discussion there for the moment and move on to one-words theories. So the actual motivations for worrying about the quantum reality problem, to my mind, are that we want to find a mathematically precise, physically natural, and empirically confirmable description of an ontology for quantum theory. I'll say precisely what I mean by an ontology in a couple of slides. But I want to draw an analogy between something that almost all physicists agree about and the reality problem. It's generally agreed that we should be looking for a unified theory of nature that includes the forces that we do understand, should also include gravity, should presumably have some account of dark matter and so on. And almost nobody thinks that it's just fine to write down what we do understand, something like these terms, and then add a plus sign and say, well, there's something extra small, and we don't understand that bit, we can't precisely define it, but that's my unified field theory. Everybody understands that's a cop-out. That isn't what we mean by unified field theory. It's just not an attractive proposal. It's not a credible way of advancing science. And when we look at it, if we're looking for an ontology for quantum theory, we should again be looking for something that's mathematically precise as well as physically natural. Quantum theory is a probabilistic theory. A mathematically well-defined probabilistic theory needs in particular a probability space. It needs a sample space. What are the sets on which the probabilities are defined? The ontology is the set of those possibilities, omega, and we should settle for no less precision when we come to trying to define the ontology than we demand when we're looking for dynamical laws. And if we had such a thing, and it was elegant and natural, mathematically precise, realist, since it defines an ontology, and includes all of fundamental physics, then we would have the holy grail of fundamental science. We would have a conceptually clear route to explaining, at least in principle, how everything, dynamics, randomness, cosmology, an account of the past, an account of human evolution and the evolution of life on Earth and perhaps elsewhere, follows from a single set of postulates that are all testable and confirmable by standard scientific methodology. That seems to me a grand scientific goal that we shouldn't lose sight of and we should continue to strive for. I'd like very much to know whether we have to change quantum dynamics in order to find relativistic solutions to the quantum reality problem. Dynamical collapse models are one line of thought that suggests quantum dynamics does need to be changed, but they're not the only line of thought. And we should also want to know whether we can change quantum dynamics, whether quantum theory is an island in theory space, as Scott Aronson puts it, or not. So that we could produce an interesting class of testable alternatives to quantum theory and to quantum gravity. So what would a solution to the quantum reality problem, phrased this way, look like? Well, ideally, it would be Lorentz covariant. We don't want to break special relativity. And it would give us definitions of some sample space of configurations of, and I'm going to use Bell's word here, beables, as a sort of placeholder for whatever the right ingredients in the theory are. These could be events, they could be histories, they could be paths, there could be some other mathematical object that define elements of physical reality. And a configuration of those things gives a complete description of physical reality. And then we need a corresponding probability distribution on that sample space. And all this should work for closed quantum systems that serve at least as good models of the universe. And ideally, the ultimate aim is to have a version of this that works within a verified cosmological model to the universe itself. If we do that, then our story of nature runs like so. What is physical reality? Well, it's one of these configurations, one such configuration from this set. Which one? We don't know, but we do know the probability distribution, and we know that it's randomly chosen, drawn from the sample space. And to test this, to validate it empirically, it should imply quasi-classical physics in realistic models. In particular, it should imply the theories that already work very well, Copenhagen quantum theory and classical dynamics, in the domains where they work. We have something like this. Our theory is a set of configurations C, and a configuration includes enough data about the elements of physical reality to describe the cosmology and describe Earth and the events on Earth and the events of our daily lives and so on, and probabilities P on each C. There's another discussion that I'm going to sidestep here. Do we really know what one-shot probability means? Is there a problem with the foundations of probability? I want to acknowledge there's a real debate on this. To my mind, that debate can be satisfactorily resolved by Kolmogorov's account of probability in terms of algorithmic complexity. But again, that's a long discussion, and I don't want to take up the precious time we have here with it. So one gets many objections if one sets out the quantum reality problem this way. And the first couple are, we're not in any position even to start this program. We haven't got a mathematically precise definition even of relativistic quantum field theory in Minkowski space. And beyond that, if we really want to describe cosmology, we need to include gravity, and then we need a quantum theory of gravity, and we haven't got a well-confirmed quantum theory of gravity either. And both of those points, of course, are correct. Alas, we can only give what ultimately are unrigorous, although widely shared, intuitions and formal definitions of what relativistic quantum field theory is. But that will achieve a lot. That can reduce fundamental conceptual problems to already known technical problems in trying to make relativistic quantum field theory more rigorous. To the second point, well, absolutely, whether we need quantum gravity or not is actually, as is being discussed elsewhere in this meeting, very much a live issue. We need some unification of quantum theory and gravity, which could be a conventional quantum gravity or could be something else. Understanding quantum reality gives one way of trying to construct unified theories of quantum theory and gravity. So in that sense, what I'm calling the reality problem, the measurement problem, is a motivation, a potential springboard for progress elsewhere in physics. And also for making sense of quantum theories of gravity. And very much the other way around. I think it's very much an open question whether progress on the measurement reality problem will come from quantum gravity or vice versa. Both lines of thought are absolutely vital, and they should both be being pursued. Let's be clear, this isn't just a problem for people who are worried about the quantum reality problem. Every approach to quantum theory has these problems. Everettians, for example, have these problems if they want to give a detailed story about the universal wave function. All right, so I tried to suggest the quantum reality problem is a problem in fundamental physics. And I want to suggest that it's a problem that's likely to motivate new physics, not just new metaphysics. And I want to, because I want to reflect my own view here, which is a certain amount of open-mindedness on exactly where the solution is going to come from, and so where should we be looking. So one regime is indeed the interaction between quantum theory and gravity. If you look even at quite recent reviews of quantum gravity online, they say that the quantum gravity scale is so remote from current experimental abilities that empirical tests are near impossible. But as we all know by now, that picture changed quite radically in 2017 with a couple of seminal papers, and in particular this one by our colleagues, Sugata Bose and collaborators, who identified a completely new class of tests, and I'm going to be careful about how I phrase this, tests of the interrelation between quantum theory and gravity, which are sensitive to the gravitational constant in h bar, but not sensitive to C, and open up a much more accessible experimental regime. And that's extremely exciting for many reasons. Here, which I guess is familiar to pretty much everybody by now, is the basic idea of their experiment. One has two small masses, both created in position superposition states, in interferometers that are closely aligned so that the masses fall alongside each other, and their gravitational interaction, weak though it is strong enough that it's capable of entangling them. So one line of thought is, well, those experiments should certainly be done, and of course there's a huge and very active program pushing the technology towards the point where we're able to do them. But in the meantime, there are potentially simpler and easier experiments that could already give us strong evidence, maybe not about everything that those experiments can test, but evidence about whether quantum gravity or some competitor theory, something else, works in a relevant regime. So I have a couple of ideas of my own that I highlighted on this slide. One line of thought involves setting up something like a Bose-Marletto-Vedrel experiment, but with a further layer of entanglement between this particle and something else. It could be a photon that's entangled and somewhat separated from these two interferometers. And the photon is measured at some point, and the question is there some effect of the collapse of that measurement? So there are motivated approaches to quantum reality in which collapse propagates at light speed, and an experiment like this can test that in the context of these experiments. A second and probably easier thing to do is to test the old idea of Müller-Rosenfeld semi-classical gravity in regimes where it hasn't yet been falsified. So tested in the mesoscopic regime. And the thought here is that we have an indeterministic quantum measurement, and that either does or does not, or said more precisely, creates a superposition of two states in which a small test mass either is dropped or is not dropped alongside one of these interferometers. And if semi-classical gravity applies in this regime, then the interferometers, whether the mass is or is not dropped, which one can measure later, the interferometer doesn't see the gravitational effect of the mass, nor the gravitational effect of its absence, but the average of those two things. So this would test whether there's a single gravitational field in the region of this experiment, as semi-classical gravity would predict, but standard intuitions would deny. And that's an important ingredient, that's an important foil that the original BND experiments are trying to exclude. And one that I think we should be able to exclude, or of course, if we get very lucky, confirm much sooner. So one place to look for new physics, partly motivated by the quantum reality problem, is in tests of quantum gravity. Another line of thought, which I think is going to be very well reviewed later in the meeting, is the thought that collapse itself is an intrinsic physical process, and we should be looking for mathematical models that characterize the nature of collapse. So this is, I think, a very interesting line of thought. It was maybe the first, after Bell's theorem, the first really fertile connection between quantum foundations and experimental physics. And it's been very well developed over the years by its pioneers, Ghirardi, Rimini, Weber, Pearl, Nicolas Gisin has contributed a lot to this topic over the years. Angelo Bassi and collaborators have been pushing the theory and experiment forward lately. To my mind, collapse models are a very well motivated idea. They're almost certainly wrong in detail, but they might not be completely orthogonal to the truth. So the motivation for experimental tests of collapse models, I think, is very strong. It's that one might pick up something that, because the collapse models are along roughly the right idea, one might pick up some deviation from quantum theory. And once you have experimental data, you could figure out actually what that deviation is telling you, and hopefully build something that's a little more persuasive than existing collapse models. Without going into detail again, I just want to stress to my mind that although most attention is focused on a particular class of collapse models, there's actually a wide range of alternatives out there. I have a somewhat different type of collapse model of my own that I've sort of tried out. There's a paper on the archive from a few years ago about this. And there are even recently a revival of the idea, Wigner's old idea, that consciousness should somehow be involved in the collapse of the wave function. Why do we need collapse of the wave function? Because observers need a different outcome. What's the point of observers? It's to be there in physics in order to cause collapse of the wave function and give completeness to our otherwise incomplete account of physics. So various authors, including, I guess, the best known, David Chalmers and Kelvin McQueen, have set out pretty tentative ideas. I don't think they're remotely gung-ho about these ideas. Their ambition is modest. Here is a line of thought that deserves to remain on the table as long as we haven't got a good understanding of the measurement problem or the reality problem. And along with that, there's been an upsurge of interest in the general question of how consciousness and physics connect. So that leads me at least to devote a slide on whether we should be looking at the role of consciousness in connection with quantum reality in trying to motivate new physics. There's certainly some beautifully written and well-argued books. David Chalmers' classic, more recent book trying to revive Russell's old idea of panpsychism by Philip Koch, and others that argue for a view of consciousness that's in one way or another potentially interventionist or interactionist, in which consciousness does more than simply come along for the ride. And in order to fully understand physics, one needs to include an account of consciousness. Alongside with this, although with very different motivations, there's what's become a well-known theory of consciousness, integrated information theory by Tononi and collaborators, on which indeed the model of the previous slide, consciousness and collapse of the wave function, is built. And there's even been some work by people at Google motivated by an old classic paper of William James's, which I have to confess I've long found very inspiring, looking for the possibility that somehow consciousness plays an interactionist role, and that one might be able to find hints of that in the output from small quantum computers or small quantum robots. As far as I know, they have found no hint of that so far, but it's interesting that people at the frontiers of quantum technology are taking these ideas seriously enough to actually be looking for anomalous effects. I suppose my view on this is these ideas have enough motivation that one should be searching, not enough motivation that one should be very confident about finding certainly any specific type of answer or perhaps any deviation from physics. But that But the first point, I think, is the strongest point. There's enough motivation there. There's enough intellectual uncertainty about how consciousness fits in with the rest of physics that we should be looking for motivated ideas that connect consciousness and quantum reality and looking for empirical tests. That fits into a broader view that I guess I align with these days, which is there are several motivations for expecting some new physics to arise from questions connected with the quantum reality problem. I touched on 3 or 4 of them: connection with gravity, quantum reality problem itself, so the need for an ontology, and the connection with consciousness. Perhaps we should be not focusing on our favorite one of these, because perhaps we don't have strong enough reasons to pick out a favorite one. But rather we should be looking for general ways in which quantum mechanics can be varied that are testable. So I'd like to spend a few minutes fleshing out that line of thought a little bit. And there are a few papers that I've written over the years along this line of thought. So here's the line of thought in a nutshell. If we accept that we need a precise ontology and that we need something that we don't yet have, some mathematical ingredient that we're going to call beables, which have some probability distributed configurations that constitutes the solution to the measurement reality problem, then we have an easy way to generalize quantum theory. So the thought is a solution to the quantum reality problem that doesn't do anything to quantum dynamics gives you some set of probabilities on the beables. In the same sort of way, in the non-relativistic setting, de Broglie theory gives you a set of probability distributions on particle trajectories, but doesn't alter quantum dynamics. Standard de Broglie theory doesn't. So we have these probability within standard quantum theory of configurations. But instead of those, we could take the probability weight of the configuration to be something that depends not only on standard quantum dynamics, but also on some structure of the configuration itself. In principle, this can be any non-negative function. So we now reweighted our probabilities, and so we have to renormalize by summing over everything. But we can do that. It's do more general things, but this is already such a large class of generalizations that I think it's fine to focus just on this class for the moment. So if you take this way of generalizing quantum theory seriously, you realize that you're led to a new class of laws of nature, at least laws of nature that are not standardly discussed. What this weighting factor does is give some statistical constraint on quantum evolution that isn't there in the initial state, and isn't there either in the Hamiltonian dynamics. And it's not always thrown away the Hamiltonian dynamics, that's still there. But there's an extra weighting factor that says, well, work out what the Hamiltonian dynamics would have implied, and then reweight it. So we have, and I'm going to use the term hodological types of law, in which, for example, the evolution can be guided towards particular types of paths in configuration space. The term hodological comes from the Greek for path, hodos. This sounds like complete chaos. It sounds like the abandonment of science when one first comes across that idea. But it's just not. If the theories are simply phrased, and they can be, they can have explanatory power, and they can have explanatory power when you think about it carefully, in just the same sense that the more familiar Newtonian paradigm, which involves an initial state and an evolution law, has. So, to build a little bit of intuition about this, we can use a very, very simple model, the old Ehrenfest-Stern model, and just put constraints in the model. So let me remind you how Ehrenfest's modeling statistical mechanics has a model in which you have, in its simplest form, you have two urns and you have a number of numbered balls. And at each time step, you choose a random number, so here from 1 to 10, and the corresponding ball is moved from whatever urn it is to the other one. So in this case, I think ball number 9, no, one ball has moved across from the right hand to the left hand. Actually, this was not a single jump, so this is after a number of jumps. Balls have moved across from the left to the right, and after a number of jumps, we've ended up with 6 balls in the left and 4 in the right. And if we carry on jumping, we'll see fluctuations. And in the standard model, which is supposed to be a simple model of standard statistical mechanics, we expect fluctuations mostly about the equilibrium. And you could sort of see that to some degree credence, at least even in this simple standard run. These things are fluctuating quite a lot of the time about the equipartition distribution, and they're not getting towards the extreme distributions, at least not so far. So if we incorporate weights into the Ehrenfest model, we can modify it by saying, well, we're going to do that, but we're only going to accept an outcome that satisfies our weight criteria. So if our constraints are strong constraints of this form, if they say, for instance, that the number of balls after 10 steps should be precisely 5, and then the number of balls after 20 steps should be 5 again, we run through an Ehrenfest ensemble, and maybe there's only 3 balls here, then we throw that away and say, well, we'll start again. And we keep going until we get a run that actually satisfies the constraints. Starts at 5, is 5 in the middle, and is 5 at the end. A boring example, but a slightly more interesting example would be one that involves weighting towards a particular path. So the path here is this red line, and we've got here a model of something that's, I suppose, a toy universe, which is being guided towards going from equipartition, 5 balls in each, towards a final state in which all the balls are in one urn and none of them in the other one. But it's being guided, it's not being forced. So that we have a weighting factor, basically a Gaussian factor, that says, what's the probability of a given run? Well, it depends on its unweighted probability times this factor. So how would you model that on a computer? You would do 2 things. You would first draw out a run, and then you would calculate this value, and then you'd roll a dice. And suppose this value is 1 in a million. Well, you roll a dice, and only with 1 in a million chance would you accept it. Otherwise, you reject it, and then you start again. But eventually, you'll find a run that you accept. And if you do that, you get this sort of picture. So the runs that have been accepted are in various colors here. So I'm just tracing out one of them. And you can see they're being guided by this red line, but they're not following the red line precisely. I should say there's a precursor to the discussion in a very nice old paper by Gelman and Hartel, who were interested just in the time symmetric case of initial and final states. But I want to generalize their thought here. So the cosmological implications of this are, once we have a realist ontology, we can incorporate pretty much any statistical constraint on a cosmological evolution or into a hodological version, a non-standard version of quantum theory. So for instance, you can imagine a weight function that forces your universe to grow to a particular size, forces it to attain a particular degree of homogeneity, and forces it to do that successively at various cosmological times in ways that would be unlikely if you were just working with the initial state and the Hamiltonian. What are these things? Are they foils or are they competitors? Well, the conservative view would be they're foils. At the very least, it would be very nice to say we have a way of strongly confirming that the Newtonian paradigm works in cosmology. And to do that, we need something, even if we don't really believe it, something against which to test it. And these models, suitably parameterized, give us those tests of the Newtonian, tests against the standard Newtonian paradigm, so that we can parameterize just how well have we confirmed it, how well have we excluded these models. It's been taken, and I guess this is the view I would take, as genuine competitive theories to standard quantum theory. And so it's crucial here. If you take ontology seriously, if you take the quantum reality problem seriously, then it should take sufficiently elegant theories, not all theories of this type, but sufficiently elegant ones that involve few parameters, seriously as potential competitors. And the reason is you kind of expect if you have a whole extra layer of mathematical objects that define your ontology, there's at least a fair chance that it has its own physical effects. That it's not purely what the philosophers call epiphenomenal. It's not just coming along for the ride with standard quantum theory. It seems actually a little odd that physical reality would be probabilistically determined by the evolving quantum state, but has no effect at all on it. So we don't want Baroque theories. We don't want a theory that says, well, the universe is forced to create something like the Earth, and after 4 billion years, life on Earth, and this meeting. That's not science. Recapitulating the data isn't a scientific accomplishment. But a very good way of characterizing what is a good scientific theory, in the language of Solomonoff induction, and I'm just going to touch on this here. There's a trade-off between elegance and data fitting, which can be made precise by Solomonoff's theory of induction. And homological theory would be the very best scientific explanation of the data if it minimizes, in some way of formulating things, the length of the program that's needed together with the length of the string that's needed to describe the data. In other words, it's relatively elegant, but it also fits the data relatively well compared to any alternative, including the Newtonian alternative. So a program looking for theories of this type will tell us whether our best theories really do involve initial states and unmodified quantum probability laws. And if so, that's because they minimize description length, not because that is beyond question the intrinsically right way to do science. If we ever find what seems like evidence for a law like this, we're going to look for deeper explanations. Maybe we're missing some underlying mechanisms, some variables. There would be a lot of debate, a lot of very, very justified skepticism. My point is just that the hodological paradigm could ultimately survive such skepticism. Strongly motivated though skepticism would be. One shouldn't insist a priori that there has to be an underlying explanation for any hodological law. It could just be a brute fact about nature. So I have a whole collection of ideas of my own about the quantum reality problem that fit into this paradigm. But I won't focus on those here because time is running out. Maybe I'll say something about them in the discussion. I hope I've managed to raise a few points that people agree with and a few provocations. And I look forward very much to hearing Nicolas' presentation and then the open discussion that's going to follow. Thanks very much for your attention.
So Adrian, thanks very much for finishing well in time. And we'll now move over to Nicolas' presentation, and then it will be after 45 minutes, we will have a discussion session. And then we'll have a coffee break of 15, how many? Half an hour. Coffee break of half an hour, and then we will join. Hello, Adrian, are you hearing?
Yes, thank you very much, Dipankar. I'm
Yes,
looking forward.
Yes, so 4:30 p.m. in our time, we will be resuming our discussion session. Okay.
Not responding. How did it go? Post control.
Is that not? Maybe I can already start. Can you hear me? Yeah. Because I don't need a screen for my start. Yeah. Yesterday I forgot to take with me this famous random number generator, you know, the one that I presented yesterday that are in these Samsung phones. And so I'm just going to let them go up from, well, in each of these rows so that you can see them. And you also have a QR code if you want more information about them, just to convince you that they really exist. I don't need this one. Okay, so, well, thank you very much. Thank you, Adrian. Adrian disappeared, but I guess you hear me somewhere, Adrian, in this cyber world. And yeah, so indeed, I think Adrian and myself, we don't disagree, so maybe that is less interesting, although we have different views anyway, so there will be enough material for discussions. So you see, I changed a little bit my title compared to what was announced and also compared to Adrian, in the sense that I put quantum into parentheses, because I want to argue, or one of the points I want to make, is that this is not really a quantum problem. The measurement problem is a measurement problem. I'm going to define it and so on, but it is not necessarily specific to quantum. And the main lessons are here. So first of all, there's no reason to give up realism. So on this point of view, I think Adrian and myself, we are fully aligned. I think in this paper, I have an argument, non-realism, deep thought, or a soft option, and there you can understand why I'm deeply a realist. However, the second lesson is written here. One should give up determinism. And this, I think, I already explained and motivated yesterday when I talked about Bell inequality violation and non-locality. In order to violate Bell inequality without signaling and without infinite speed, you need randomness. So you have to give up determinism. Okay, so let's go to this quantum measurement problem. So maybe one way of formulating it is the following. How could an apparatus made out of ordinary matter not obey the superposition principle just because of a sticker saying measurement apparatus? Measurement apparatus is just a large bunch of atoms, okay, saying measurement apparatus somewhere. There's no reason to apply different physical laws or rules to that kind of bunch of atoms a priori than to any other ones, like, I don't know, the atoms or the air molecules in this room. And if you believe in reductionism, and reductionism is, of course, let's say, a methodology, and it is a super, super successful methodology. So we should not give up reductionism too easily. But maybe also it is not ultimately entirely correct. But so if we want to stick to reductionism, then there should be some kind of magical configurations of atoms and photons to which the superposition principle does not apply. So suddenly, with this kind of configuration, boom, it makes a measurement apparatus, and the laws of physics differ for this kind of magical configuration. Of course, the alternative is that the Schrödinger equation is not the entire story, and we come back to that. So this is, let's say, the quantum measurement problem. And now I want to talk about the deep measurement problem. And I think it's the measurement problem, again, I'm not saying the quantum measurement problem, the measurement problem in general is extremely important for the following reason. So what is physics? So one way certainly of characterizing physics is that it's all about extracting information about how nature does it. You know, we want to understand nature. That's the main goal of science, and particularly of physics. We want to understand it. So how does it do that? And what does it mean, extracting information? At least for a physicist, extracting information means performing measurements. So we need to perform measurements, no doubt about that. And yesterday it was functioning. And so a physics theory, quantum, classical, post-quantum, whatever, must tell us what is measurable and how, at least in principle, one should perform measurements. Quantum physics doesn't really do that. Quantum physics doesn't tell you anything. It just tells you, if you're doing a measurement, then you have to apply that rule. But it doesn't tell you what it means to perform a measurement. So that's part of this measurement problem. What is going on? Yesterday that was functioning perfectly. Okay, so in summary, the quantum measurement problem is a serious physics problem, in the sense really that without a resolution, quantum physics is not physics, or quantum theory is not physics. So this is a very strong statement, and I'm sure that not everybody will agree. Maybe you are polite here and you will not shoot at me, but I mean out there will be people who will be very, will not agree with that kind of thing. But I think indeed it's very strange that quantum theory is considered as a physics theory, although it misses actually one of the main ingredients of any empirical sciences. Somehow it works because we all have enough intuition, especially the experimentalists, to know what a measurement is, so we work around the problem. So indeed, of course, quantum theory is physics, but it's not a kind of finalized theory. And maybe one more point. I think I'm going to go with my hand because that's really. I also believe that, and I will insist on that quite a lot today, a resolution will lead to new physics. By this, I mostly mean that too many people are just talking about the measurement problem without making any progress, by the way, without making any proposal to get to new physics, to make a prediction. If you make a prediction, at least you can be wrong. If you make no predictions, it's not that you are correct, it's just that you are not doing science. So we need a solution, we need to make progress, but the progress will lead to new physics. This is something I'm very deeply convinced about. Continuing on this deep measurement problem, one statement, very simple, measurements have outcomes. If you have any doubt about that, go and talk to an experimentalist. Now, if measurements have no outcomes, the meaning of measurement doesn't mean, it means nothing. So measurements have outcomes. By saying that, I have already killed the many-world interpretation. But measurements have outcomes. Believe me, I have made enough experiments, and ask Harald or ask Peter, measurements have outcomes. That is absolutely essential. Realism. So here I try to define it, but there are many ways of doing that. But, the world out there exists and functions independently of humans. Of course, humans can act on the world, but the world would also exist without us. simple kind of characterization of realism. But as John Bell said, the world didn't wait for a PhD to start existing or evolving or collapsing or whatever you want to phrase it. And the other point, very important here, all physical theories require interpretations. Also classical physics, and I will emphasize that. You know, you will never have, and I hope the teachers here will never start a course on physics just by writing a bunch of symbols and saying this is an equation. That is not physics. Of course you can do that, and then you're doing mathematics, and mathematics is interesting, but it's not physics. In physics you need to tell stories. So if you write some equation, you have to say this first symbol means, I don't know, the mass, the velocity, the state, or something, a probability or something, but it has to mean something. It's not just a symbol. So you need to interpret your symbols and your equations. So all theories require interpretation, because physics is not only about mathematical models and sophisticated technologies. Understanding requires telling stories about how nature does it. Il faut que j'arrête avec ce truc. And maybe something also, and here I'm addressing mostly the younger guys here. I would not advise that you attack the measurement problem heads on, because it is very possible that when you will be my age and retired, the measurement problem will still be unsolved. It's a possibility. So don't spend your entire life working on that and only on that. Of course, I would also say, don't spend your entire career not thinking about foundational problems. Do both. And do both because at some point you will like to have a salary, makes sense, and society is going only to pay you if you are kind of useful. And secondly, I also think that there is a much larger chance that you're going to produce something useful, including to solve these deep problems, if at the same time you do some solid physics. Because these solid physics and the more fundamental questions, they really feed each other, and in the second half of my talk I will essentially illustrate that. It really feeds each other, so don't spend all your time on one side or all your time on the other side. Refuse to get into one of these categories. I know that in general people like to put you in boxes, but refuse and resist to be put into a box. So here you have a chaotic system. We all know about that. And usually, according to classical mechanics, so now in classical Newtonian mechanics, we understand that as deterministic chaos, isn't it? But is it really so? Or is it a consequence of some form of interpretation of classical mechanics? So here the system is too complicated with this Brownian motion, so let's simplify, and I'll take just, okay, what is known as the Baker map. So I have just the state space is just a number between 0 and 1, so very simplified. And let's say this is the probability of sun or of rain. So 0 means it's sunny, 1 means it's rainy, and it can be anything in between. And then there is an evolution, and discrete time in this case. So you stretch it, and then you bend it back, fold it back. And this, if you write the state here in binary form, so it will be a number between 0 and 1. So it starts with 0, dot, and then you have a bunch of bits here, write it in binary, so these are bits. And then this evolution, which I just showed you, corresponds to the following one. So the first bit you forget, the second one becomes the first one, the third one becomes the second one, and so on. So you just shift everything to the left. And here you understand that this is chaotic in the sense, in the usual sense, because this bit, which initially was completely irrelevant, no, it was far down the series, but after n steps, it will become the first one, so it will become super important. It will be the dominant one. So it's indeed very sensitive to the initial condition. Another, the question, natural question is the following one. whether so x lies on the left or the right. This is not that question. This is just saying, indeed, if whether x lies on the left half or the right half after n steps depends on the nth bit of the initial condition. And the question is whether this, let's say billion for million for whatever, a bit, one which is really far down the series, is it physically real? And the question is not whether we can measure it. Of course, we cannot measure the billionth bit, but whether this corresponds to something physical. So this is a matter of interpretation. Are you going to say, oh yes, this is real, it's really physical, or no, this is not physical because it corresponds to something which is anyway not measurable? Interpretation. You can choose. So let's look at typical real numbers. Of course, this is a number, x between 0 and 1. Let's look at some typical numbers. So square root of 2, pi, fractions, and so on. But very important if you now think of typical real numbers, not those exceptional numbers, those that have a name or an algorithm, but a typical one. So a typical one, these are the numbers where the bits are totally random. And really, us measurement outcomes. We know that measurement outcomes are random. Well, actually, take a typical real number. The bits of this typical real number are also random. So one way of thinking of them is really just what comes out of one of these quantum random number generator. And, okay, maybe here it's too simple, I guess. One thing that is interesting, I like it, that Émile Borel emphasized is that in one real number, one can code the answer to all questions one can formulate in any human language. So this is a nice illustration of the fact that in one real number, you have infinite information. And since you have infinite information, this bit string goes on forever, without any structure. So you can code whatever you want. For instance, you can code all the future of a chaotic system. You can code whatever you want. You can also code the answer of any possible question. So when we say let x0 be the initial condition, we actually say let x0 denote an infinite amount of information. So it's not such a harmless thing to say let x0 be the initial condition or denote the initial condition. Let me here just argue, but this is just an argument. I'm not saying this is a proof, but let's argue that in a finite volume, you cannot put more than a finite information, a finite amount of information. Makes sense. So let's think now of, let's say, a cubic centimeter, and we put a little ball inside. According to this assumption, finite volume implies finite information. The position of this classical particle cannot be a real number, at least not a typical real number, because a typical real number has infinite information. So let's now look at a typical real number. Here is a typical real number. Start, let's say, with a 0, doesn't really matter. And then you have, well, digits here. And I really made, when I did that, I really used actually a random number generator to make sure that this is random. And it continues. So this is really my intuition of a real number. And if we would have enough time, we could wait until the screen is full. And when it continues, it's going to cross the Earth. And it continues. And at some point, it will exit the galaxy. And it will continue. It will continue, and it will fill the universe. And it will continue. It's really infinite. That's the way I think of real numbers. But actually, classical mathematicians, they think differently. For them, it goes like that. So be careful. Don't look at me. Look at the screen. Careful. Boom. 0 time infinite information. It's beautiful mathematics. It's not physics. In physics, you will never have infinite information in 0 time. Okay? At least that's the way I say. You can have a different interpretation because classical mathematics and classical physics can have different interpretations. So you can really, here, instead of indeterministic events happening as time passes, think that all the indeterminism is coded in the initial condition. You have a choice. Or you may also say, instead of God playing dice as time passes, God played all the dice at the Big Bang and coded all the outcomes in the initial condition. So it seems that actually this kind of mathematical language, the value we attribute to real numbers, is really what is actually forcing or influencing us to speak of deterministic chaos. However, these mathematical real numbers, if we now have understood what I said, we understand that they are actually physical random numbers. Or the way I like to say it is real numbers are not really real. So which interpretation would you prefer? Of course, you have the choice. But let's go to the real physicist. And one of the very hot topics in physics today is the simulation of the climate. How do these people do that? So they have huge computers, but finite computers, of course. And so what do they put in? They put initial conditions, but they don't put a typical real number in it. They put a truncated number. They take all the data they have, they put it in. And then they start running their simulation, and pretty quickly, they need bits or digits that are not yet there, because they are the very, very small digits initially, but this is a chaotic system, so this is super sensitive to the initial condition. So these little bits or digits become relevant. So what do? They add stochastic reminders. So these people do understand and use real numbers exactly the way I showed you, where one digit comes after the other. And you don't need to put everything at once in it. You put it as you need it. That's the way real physicists do it. And so it should be these random numbers that lead us to believe in deterministic chaos. Okay. So in summary, whether Newtonian classical mechanics is deterministic or not is not a scientific question. It depends on the physical significance one associates with mathematical real numbers. So it depends on interpretation. So here the main message is that the measurement problem and interpretation, and I will come to hidden variables, this is not something specific to quantum. It is specific to science, and particular to physics. You will always need interpretation, and you can always choose. Obviously, every indeterministic interpretation, you can say, oh, I assume that the future is in the initial condition. Brownian mechanics, you can do that. It is a possibility, but you can also stay more, use Occam's razor and see, the real numbers are not really real. So the measurement problem is not a quantum problem. It affects all indeterministic physics, because you always need to say, when do potentialities become actual? Or a different way of saying the same, when does indeterminacy become determined, or when does indeterminacy lead to events? So for me, event is something like an outcome of a measurement. It's something determined. So once you have these kind of things, you may say, okay, no, but we need to add hidden variables. At least in quantum mechanics, that's a very natural thought. But now if you start thinking that classical mechanics is also indeterministic, you may also want to add hidden variables, additional variables, and this is certainly possible. Yeah, so again, instead of God playing dice when potentialities become actual, God played all the dice at the Big Bang and coded all the results in the initial condition. And so, what are the hidden variables of classical mechanics? Well, you know them very well. The hidden variables of classical mechanics are the standard real numbers. The real numbers are the hidden variable of classical mechanics, and they are really hidden because they are really inaccessible. Infinite information, of course, no one has infinite information. So you have here an example of hidden variables. Of course, these ones are not non-local, but on the other side, they are really hidden. And maybe a sociological comment. Almost all physicists accept real numbers, usually without noticing that they are hidden variables, while the same physicists simultaneously reject Bohmian positions as unnecessary. Maybe we should be consistent and accept Bohmian positions and accept real numbers. That's okay, at least it's consistent. Or you reject Bohmian positions and you reject real numbers. That would also be consistent. Not contextual. Okay, so now could be the end of my talk somehow. I have said the essential. In the second half of my talk, I want to illustrate how one can work on the measurement problem and combine it with what I call good physics or solid physics or more standard physics. And I think indeed we'll see that there are plenty of ways of combining these two. And actually, all of this morning session was all about that. No, we were at the same time doing solid experimental physics and addressing or having the measurement background more or less explicitly in the background. So it's a good example, and I want to give you a bit more of that. So here the first point will be theoretical physics inspired by quantum field or measurements in quantum field theory. So in this space-time diagram, so time is vertical, space horizontal, we have a source, we have a receiver, and these lines indicate the light cones. So future light cones of the source, past light cones of the receiver, and clearly they don't overlap, so there must be no signaling here. At least you cannot communicate at the speed of light. However, here we are going to put in some middle region some measurement, and this measurement will be non-selective. So of course the source can communicate to the central region, and the central region can communicate to the receiver, but of course there cannot be communication from the left to the right part of the central region, or this middle region. And again, the measurement being non-selective, you don't need to communicate the outcome. And important, so for that to be possible, this central or middle region needs to have some extension in space. Horizontally, it has to have some extension. If not, you could not have this kind of situation. So now let's look at that. And okay, I'm just going to use again our Alice and Bob friends. I put Alice on the left of the central region and Bob on the right-hand side. And let's say we want to do the following measurements. The measurement, which I call the twisted basis, I mean, it's not my invention, it's called the twisted basis. And it's a strange measurement because it has the following 4 eigenstates. 0, 0 for qubits, you understand that. 0, 1, 1 plus, 1 minus, where plus or minus are superposition of 0, 0, state 0, plus or minus state 1 normalized. So you see the 4 eigenstates are product states, but this is not a product basis. It is this basis, whatever. So let's start now with state 0, 0. And the sender does nothing. So what comes out is just the state 0, 0. Now, you measure in this basis the state 0, 0. What comes out? Well, obviously, it's the state 0, 0. So what does the receiver receive? State 0. Obvious. Now, the sender is going to perform an action. The action is to flip this bit, this qubit, acting with this unitary operator. So now we have the following, 1 and 0. Now, if you enter the state 1, 0 and measure that, you will get one of these 2 possible outcome states with the same probability. Probability 1/2 for each. So what comes out is 1 on the left, plus or minus one of these 2 states. So the mixture of these 2 states is the identity. And identity is different from the state 0, can be distinguished. So the receiver can notice whether Alice or the sender did perform this action or not. So you have signaling. And so these kind of measurements are called in quantum field theory impossible measurements, and they are impossible because they are signaling. We understand that. So let's see what we can do. So we want now to realize these kind of measurements here. Coming from quantum information, we are going to say, let's use an ancilla. And as an ancilla, we are going to use 2 more qubits in some state. So this famous phi plus state is one of the Bell states. So one maximally entangled state of 2 qubits. And then we do, some Bell state measurement here. Here we'll go a bit fast. If you really want to understand that, you need to read a bit more. But you can do something locally there. And then somehow you have teleported this qubit to here, but without knowing the outcome B. So you can do something here. You undo as much as you can. And the theorem says that there are 2 possibilities. There are 2 kind of measurements you can perform in that way. One is this twisted Bell measurement. Twisted basis measurement. The other one is the Bell state measurement. So before I just showed you that if I do this twisted measurement and apply the projection postulate, I get signaling. So what is going on here? What is going on is that here we will get the correct measurement outcomes with the correct probability. So Born rule is completely satisfied. However, clearly the post-measurement state, for instance here, this will end up in a maximally mixed state. So it's very far from the projection postulate. So what we learn is we have disentangled in a measurement process the part of going from quantum to classical with the appropriate probability given by the Born rule and the collapse of the wave packet. These are 2 different things, and here clearly we can do one, but without doing the second one, because the second one would necessarily lead to signaling. Okay, and here there are some results due actually mostly to Lev Weidman, but other people also, that says that actually all measurements in any dimension, any number of parties, can always be localized, like we did for this twisted basis. I just here want to illustrate another thing, another learning from this way of combining measurements and good physics. Let's suppose now you have a second ancilla, again, a second time a phi plus state, and you do the following. So you do a Bell state measurement here, a Bell state measurement here, and then using the outcomes, the local outcomes, you apply a local unitary here, and here also you apply this local unitary, these Pauli matrices. Then actually, you have also performed the Bell state measurement. So the Bell state measurement can also be localized that way, but even in an ideal way in this case. By ideal, I mean is one where the projection postulate is exactly satisfied, except maybe that you need to swap this qubit with this one and this qubit with this one. But up to this 2 swap operator, you have now an ideal measurement satisfying the projection postulate. But then there is this theorem that says that the Bell state measurement is the only non-local measurement of 2 qubits that can be measured ideally without signaling. And this is something important because it tells us that the Bell state measurement is not at all a typical measurement. It is exceptional. It is unique. It's the only one that has this property that you can actually measure it ideally between Alice and Bob at a distance. And so the consequence is that you should not base your intuition of joint measurements on the Bell state measurement, because everything that you are going to learn from the Bell state measurement is actually exceptional. So who knows any other joint measurement of 2 qubits? There are, of course, a continuous infinity of these. Can it be that no one knows any? I know that you know some. But so you see, another lesson is we should know way more about joint measurements, measurements that have entangled eigenstates. Okay, but here I want to go fast. Okay, here is a measurement that is indeed different from the Bell state measurement, which I call, okay, the elegant joint measurement, because, so it is entangled, you have it written explicitly here, and the partial states points towards the vertices of this tetrahedron. So it has a lot of symmetry, so it's nice. And that's maybe the best I could tell you about elegant, about joint measurements different from the Bell state measurement and still having some structure. But one of the open questions is the following one. I don't know, and I don't know anyone who knows, a measurement which we could call elegant or natural or I don't know, something we would like to know on n qubits. This is no longer the measurement problem per se, I agree, but it concerns measurements, quantum measurements, and somehow, you know, how can it be that we don't know that actually, well, maybe we're just too shy, but no one dares even to mention a single joint measurement different from the Bell state measurement when we know that there is a continuous infinity of such measurements. And now if you go to more n larger than 2, well, I guess no one in this room could mention a single one. So here you have a lot of possibility to make good physics while working on quantum measurements, even if this is not the deep measurement problem. So let's now assume that the Schrödinger equation is not the full story, not more than Newton's equation. What can you do? So when do potentialities become actual? So I'm coming back to this question. One possibility, and we heard already a bit this morning about it, and I think there's an entire session also tomorrow, spontaneously, these spontaneous collapse models. That's certainly a possibility. A second one could be that, well, when special conditions are met, I will spend more time on that one, because I think it's a bit more original. And the last one, maybe when higher order level require it, like in the Copenhagen interpretation. Very vague. What does it mean? I can write it. I mean, I guess the grammar is more or less okay. One understands what is written formally, but I don't think we understand really what higher order level mean. But anyway, and notice again that only option 1 and 2 are compatible with reductionism. It's quite strange also that actually most physics pretends to use a Copenhagen interpretation, which is not reductionist. And at the same time, the same people will claim that they are reductionist. So most physicists, again, are not consistent. So modified Schrödinger equation. So the measurement problem arises from the linearity of the Schrödinger equation. So if you want to make it nonlinear, then we face the fact that was mentioned also this morning that all deterministic nonlinear modification activate quantum non-locality. So again, we need to remove the determinism here. And so we need a stochastic nonlinear Schrödinger equation, which was written explicitly this morning on the board, at least for this continuous spontaneous localization model, but you can make it way more general. And here I have just an example of the solutions, so not of the equation, but of the solution. So you start with some superposition of photon number state, I think, yeah, all the old ones, so 1, 3, 5, 7, and 9. You let it evolve. Because it is stochastic, it will evolve differently, like for Brownian motion. And you see that after some time, it stabilizes on one of the eigenstates. So here it's simulating not position measurement, but photon number measurement. I'm not going to say more about that, but I think this is really a very, very interesting line of thought, and maybe during the discussion I can also tell you why. At the same time, I find it also quite disappointing. A second illustration, combining again deep measurement problem with the idea that the collapse should happen, or the transition, I should not say the collapse, but the transition from potentialities to actualities happens when some special conditions are met. And as we heard this morning, one idea that is pretty popular today and makes some sense, it doesn't need to be correct, but at least it makes some sense, this is connected to gravity. So here you have again this usual scenario of a Bell test. You have the inputs, and then you have the outputs that come, and you have the light cone. So we have space-like separation between Alice and Bob. And we could say, we can ask, when is a quantum measurement finished? We had this question also yesterday. And one possible answer is that actually a measurement is finished only once a macroscopic mass has significantly moved. You know, that's really inspired by these Joshi-Penrose ideas, some more, but you know, let's see, when you have your detector, in the detector, maybe you just have a few electrons, or even you have a billion electrons, but billion electrons is not much mass that move, and that's not enough. Maybe you need, I don't know, your hard disk to start moving. Okay, today we don't have hard disk any longer. So you need maybe to wait a bit longer until something is going to move, some mass is going to move. What can we do with such an idea? And here actually we can come back to Adrian, who noticed, years ago, that according to this plausible Joshi-Penrose kind of idea, no Bell test so far has ever ensured space-like separation. Because what is actually happening, the measurement outcome is not coming out here, it's coming out here later, because you have to wait until some mass moves. And so actually we never tested really Bell in space-like separated configurations. So if you now start from this kind of thinking, clearly inspired by the deep measurement problem, you can also do some good experiments. Because now you say, okay, I have my standard Bell inequality test. So interferometer, so this is not polarization because I'm using optical fibers and so on. I have my avalanche photodiode, so this is my single photon detector. But in single photon detector, according to this assumption, there is no collapse, so there is no quantum to classical transition, from potentialities to actualities transition. But I electronically turn on a piezo, and this piezo is going to push a little mirror, or push a little mass. And if you do that, you can, first of all, notice that here at time 0 is the time when the single photon detector fires, but here we are only these electrons, so not enough mass. Now you start pushing this little mirror here with your piezo, and after 6 microseconds, you have pushed it by 12 nanometers. So it takes some time. So clearly we have delayed the measurement outcome by at least 6 nanometers. But then it also takes some time, according to Joshi-Penrose, for the collapse to really take place. And according to their numbers and model, it takes, for our case of the mass, is 2 milligrams and so on. It takes 1 microsecond. So altogether, it's 6 plus 1, 7 microseconds. However, in our case, we had 18 kilometers B-line separation. So that corresponds to about 60 microseconds. So we were on the safe side. We had a visibility 90%, so plenty enough to violate CHSH. And so we can kind of claim that this is the unique Bell inequality test where we really ensured space-like separation. Now, of course, I don't want now to start arguing with Harald or anyone. It's just here you come with an assumption, a very clear assumption. Okay, going back to Joshi, Penrose, and then Adrian had the basic idea. And you do an experiment, which is clearly a valid, a good experiment. Makes sense to make this experiment. And you say that, okay, maybe the Joshi-Penrose model is simply wrong. Or even if it is correct, for sure this is not going to explain away non-locality, quantum non-locality. Another example, now illustrating the assumption that the transition potential to actual happens when a higher order requests it. And there the intuition that we probably all have, although it is vague, has to do with macroscopicity. All morning we were talking about quantum macroscopicity and so on and so on. So here I have an example of 2 crystals. So here illuminated with these green and red lasers. But these crystals, they are 1 centimeter long. You can hold them in your hand. You can see them with the naked eye. There is no doubt that these are macroscopic objects. Looks like a piece of glass. Although it's a crystal, never mind. And actually it's a crystal which is also doped with rare ions. But it looks like a crystal. And you can put them in a cryostar and have some macroscopic distance. Okay, in this case, it was not large, just 1.3 centimeters. And you can entangle them. And you can even entangle them such that you can, at the end, use this entanglement to violate some Bell inequality. So the question is, does these 2 entangled crystals count as macroscopic quantumness? So it's a good question, no? Is that, or should there be? So since we saw Bell inequality violation, clearly there was no collapse or no decoherence here, but they are macroscopic. So what is going on here? So quantum means entanglement, and we have entanglement, no doubt. But do these count as large entanglements? And here I think the answer is no. Although the crystals are large, they have also billions of these ions, of rare earth ions, so it's really an object that includes an enormous number of quantum objects. The reason I'm saying there is no large entanglement, because here we had only one delocalized excitation. So you really had one photon being absorbed in these crystals, or actually it's even a bit more, it's even not one, because you have one photon arriving here with this beam splitter, and the photon then goes in superposition of here and here, so it gets absorbed in superposition of being absorbed here and being absorbed here. But it's only one excitation, or superposition between 0 and 1 excitation, so very low number. So the answer is that this is certainly not macroscopic entanglement or macroscopic quantumness, but, and again, that goes also along what we heard this morning, when we talk about macroscopic quantumness, that has really many, many facets. And so when we say that, or when Copenhagen tells us that when it becomes macroscopic, then you have the transition to classical or transition to actualization. This is extraordinarily vague and badly defined. So we need something more. What could it be? So you could say, okay, for 2 photons or 2 qubits, we know that very well. We could now make one big one and a small one, or 2 big ones. Let's consider this. We stay with small ones, but we have really many, many, many. And we look at what is called entanglement depth. And then we are going to try to find physical quantities that we can measure, 2 of them, in such a way that if we are in some region, we say that the entanglement depth is just 2. So this is clearly small. Here it would be 4, I see. Here it will be 9, and so on. And so how are we going to do that? We're going back to our crystals with these rare earth ions in it. Actually, you really have something like 40 billion ions that are involved. So it's a large number. It's not 10 to the 23, but it is still quite large. And so we have our photon coming in. So we start, so all these ions are in the ground state. So this is ground state to the power n, power 40 billions. And we have one photon coming in. And if everything would be perfect, the photon gets absorbed, so it's vacuum now. And one of these 40 billion electrons is excited. Could be the first one, the second one, the last but one, or the last one. And you have here an enormous superposition. Okay, and all the phases are, okay, all these situations are in phase. So that's why I just put a plus here. And now if you have this kind of situation, of course you have some ions that are excited. Let's say the last one here. Then you can have spontaneous emission. And spontaneous emission is going to go into all directions, everywhere. These are these kind of dotted lines. It goes into all directions. And you can then measure the probability of getting this spontaneous emission. But you also have the case where actually the emission is in the forward direction. And you understand, because of this coherence, all these plus signs, that all these little kind of nano antennas, individual ions, they are all going to radiate in phase. So they're all going to add coherently their little emission. And so in the forward direction, we will get a way larger probability of emission. And so in the forward direction, we call it P2, and in the random direction, P1. Of course, you have to normalize it for the numerical aperture, but you can do things like that. And then we get these kind of results, so this P1 and P2 here. And this is the data we get, the raw data. And so according to this raw data, we can say that, okay, let's suppose, so the phases here are not exactly 1, or the phase is not 0, so that you get a plus one here. We get a bit of dephasing, or there are plenty of limitations in the actual experiment. But if we want to reproduce our experimental data, they must be, I don't know exactly which, something in between 100,000 and 1 million of ions that have contributed to this emission, at least these ones. Even if you had, let's say, 100,000 that are perfectly coherent, they would have reproduced these points. Of course, they would most likely there were more than 100,000, probably billions, but not perfectly in phase. But also this data is limited by detector noise, and detector inefficiency. So if we renormalize the data to take into account detection inefficiencies, we get to here, and so we can certify 16 million of ions. So now in this case, we have really a pretty large number. 60 million is pretty large. Is that now macroscopic or not? No, because again, you have entanglement. Again, you can use all that, and you can still violate Bell inequality at the end. So we still don't know what exactly macroscopic means. Maybe to contrast it with what we heard this morning had to do, and they concentrated mostly on the mass and having the mass displaced on superposition of two or more, positions. Here, I'm never displacing the mass. I'm doing purely, let's say, quantum optics experiments. But nevertheless, we try to address this question of what is macroscopic. So, conclusion. So the first thing, and very important, so a theory without a measurement model is not physics. Okay, so this is a good motivation to work on it, but also, okay, remember, don't attack the measurement problem heads-on, combine it with good physics, because I'm convinced, first of all, that it is a good practice to do that, but also secondly, that the solution to the measurement problem will lead to new physics. The other thing that we learned in passing here today is that ideal measurements, so by ideal measurement, I mean measurements that can be immediately reproduced. And so these ones are the ones that are described by the projection postulate. Or often in quantum information theory, people call them projective measurements. So projective measurements are exceptional. So the projection postulate applies very rarely. However, the Born rule that defines the probabilities, this is something which is really necessary and coming just from the linearity of the Hilbert space. So what is my opinion in all that? Okay, we can maybe discuss more during the discussion and maybe also during the evening and so on. I don't have a solution, so I'm not one of these guys who tell you, oh yes, I know. I can tell you, oh yes, I don't know, because that's the reality. But still my gut feeling is that something like a real dynamical collapse is going on. I don't know when. I don't know exactly what kind of equation would describe it, and so on. And indeed, I guess at the end, I just have to confess that it is likely that this is all more complicated than that, and that there will be a lot of good physics. Maybe just one, since I still have a few minutes, about collapse. We saw the equation this morning. Okay, that was for the mass density. You can write it also for energy or for photon number or whatever. When I worked on that in the 80s, so I guess almost all of you were not even born, I was very excited finding this equation. Wow, nice. This is the solution. Now, this equation has one enormous drawback. And this is mostly due actually to Howard Weissman, who is speaking, I don't remember, tomorrow, the day after. He is probably listening somewhere. I don't know exactly where you are. Where is the camera? Hello, Howard. Who noticed that actually the same equation can be derived if you don't assume anything fundamental, any fundamental change, but you just say the system is interacting with some environment, as it is almost always doing, and the environment is somehow monitored. I don't know exactly how, but let's say it is monitored. And then, because you monitor the environment, that has a little feedback on your system, of course, and then your system undergoes some Brownian-like trajectory in Hilbert space. And unfortunately, the equation that you get if you do this more standard physics approach, saying it's just coming from the environment, is exactly the same equation. And for this reason, it is extremely difficult to see whether you are, when you do a test, are you actually just seeing a kind of decoherence-like effect due to the environment, or are you seeing something fundamental? For that, you have to be sure that you have really isolated your system so you have no environment, how can you be sure that you have isolated enough? For instance, gravity, you will never isolate completely, and so on. So it makes it very difficult. It would be way simpler, physics would be simpler, if these stochastic collapse equations would be of a different nature from the ones due to induced by the environment. But this is the fact, and that's the way it is, and I thank you very much for your attention.
So thanks both the speakers, and I hope, Adrian, you are there. And so we meet after half an hour coffee break. 4:30. Oh, 20 minutes. Okay. So we'll aim to meet around 4:30. It went.
I thought I had until 4:04, so I was wrong in my mind. Never mind.
No, it's okay. So it went.
This thing didn't work.